All right, and very happy for us to also welcome our third speaker, Bapak Muhammad Adli Rahandi. Selamat siang, Pak Lubis biasanya saya memanggilnya. Assalamualaikum, Pak.
Waalaikumsalam.
Ya,
Hi, Bu Fitri. Hi everyone.
ya. And very fortunate all speakers who invited to deliver the presentation here in our second seminar already joined with us. And again, thank you very much for the great availability to fulfill our invitation to share your lesson work here in our participants. So for all of your information, the participant background in our not only students but also lecturers and also some practitioners from the research institute and other institutions. It would be very great, I guess, for us to have a great sharing with our invited speakers here. We would like to start the seminar at 1 p.m. So please kindly wait for the participants to join immediately with us. All right, now it's almost 1 p.m. and to the seminar committee, could you please kindly set the virtual background in our chat room? So all participants who would like to show your video also, how to say, can display, yeah, that one. Bu Mita or Bu Amel, please kindly help me for that one. And again, very welcome to all participants who just joined with us for our second seminar of World Class Professor Program, yeah, for this year. And today we will have a great time together, yeah, to how to say to listen, yeah, and also to discuss, I guess, with our three invited speaker who really how to say have a great concern on polymer composite and its applications technology. So today, as we how to say inform in our flyer, we will have three speakers. Firstly, from Pakor Nova Prakasi from Thammasat University, Thailand. And secondly, from Sung Yun Lee from KNU, Korea, Republic of South Korea. And the third is Bapak Muhammad Adli Rahandi Lubis, PhD, from BRIN, yeah, or National, I just remember the name, National Research and Innovation Agency, yeah, of Indonesia.
Yeah.
And yeah, from our record, the number of participants who registered to our program is close to 100 participants. Yeah, usually it's gradually increased. Yeah, since yeah, I mentioned 12 to 1 p.m. is just really short period for lunchtime and praying. So hopefully they will be how to say immediately join with us. Yeah, to keep this activity online, so let me try to start this meeting, everyone. And just for your information, this program is recorded, yeah, via Zoom meeting, and also directly how to say live stream in our YouTube department channel. So to the one who has any shortcoming with the how to say internet connections or other, you also can join with us and also keep interactions through the chat box in the YouTube, and then yeah, we can kindly respond later on the Q&A session. All right, everyone. So very good afternoon again to all invited speakers as well as to all beloved participants. Thank you for joining us again in our second World Class Professor Seminar. It's really great for me, yeah, especially to have all invited speakers as well as all participants here in our seminar. And today we will have a presentations from our three invited speakers that mainly will be talking about the applications of the polymer composite, especially membrane in the water treatment, and another one very typical, yeah, Pak Lubis, in the how to say biopolymers, yeah. Later on, maybe in detail, each speaker will deliver the presentation in each sessions. So for your information, the presentation will be around 30 to 40 minutes for each speakers, and then later on we will continue to the Q&A sessions. Yeah, but of course during the presentation, I would like to greatly invite all participants who has any suggestion, questions, and so on. Just kindly put your questions, yeah, in the chat room, and later on, yeah, we will discuss in the Q&A session. So let me try to start the seminar by introducing firstly our invited speaker. And the first presentation will be started by Prof. Pakor. So here I introduce Prof. Pakor again to the one who also joined with us in the first seminar. Yeah, here we really pleased to inform and also to introduce Prof. Pakor. The complete name is Associate Professor Pakor Nova Prakarsit. he is now currently in charge as the head of Department of Common and Graduate Studies in Sirindorn International Institute of Technology, Thammasat University. And also he is a director in the Center of Excellence in Functional Advanced Engineering in Thailand. And here is his educational record for the bachelor degree. He obtained from Chiang Mai University in subject of chemistry, and for master and PhD, he obtained from Penn State University, United States of America, in the field of material science and engineering, especially maybe in the polymer option. And next, please. Bu Mita, Bu Amel.
Yes,
all right, and he is this is his work experience, yeah. So up to now, I guess, as we mentioned before, he is now in charge as the director, of the Center of Excellence program there. And another record here, he also, I guess, up to now, up to now is the executive board of the Material Research Society of Thailand. Here as well, for POCON, we have the MRS for Indonesian chapter. And the host, I guess up to now still, how to say, kept by the researcher from ITB. Later on, maybe hopefully we have the great engagement, to have the connections with other colleges in MRS Thailand. And he how to say, has many significant publications, and with the good citations. And if we check from the Google Scholar or Scopus Index, his publications so far recorded around 78 publications with the H index around 17, and even he already published 9 patents. I guess maybe in the field of polymer and composite, I guess. And then next, still any information about protocol? No other slide? All right. And then here some record about his research interest. So if we see from the list, many interesting topics that he has been conducted in his research center together with his colleagues in SIIT Thammasat University. And I do believe it also will be one of your great interests as well, for participants. So for the one who would like to discuss further in detail with him, later on in the Q&A session, you can have questions or even though how to say, any comment, for this one. And then I guess, this is the record for his research interest. And then, without any more ado, Propakor, so please, now is your turn.
So thank you very much, Professor Fitri, for the nice introduction. So please let me share my PowerPoint. So does it show up nicely?
Yeah, excellent,
okay.
Prof. Yeah, excellent.
All right. So just good afternoon, everyone again. So for those that we already met during the first seminar, and also to those who just join us, right, starting from this second event, right, on our seminar series here. From last time that I share with everyone about our work related to materials that fit in with circularity concept. For today, I will focus on some work that are related to the application in water treatments and purification. So by using the materials that we develop. And this can be both fossil-based and also bio-based polymers that we use in these applications. So the outline of the talks for today, so I will mainly talk about 4 main parts. Right? The first one will be on magnetic framework composite nanoparticles, and then magnetic polymeric nanoparticles. Right? These are mainly developed and used as absorbent for water treatments. And then I also will touch on anti-scalants, especially for use in water cooling system, right? Applying the magnetic polymeric nanoparticles as well. And also we'll talk on the development of bio-based materials, right, for use as anti-scalant, especially chitosan polyampholytes materials. And the last part, I will also talk about composite membranes from chitosan materials, right? Which is our collaborative work with Professor Friti and from our WCP program last year. And I will sum up with the conclusion of the talk. And to give you the overview of the scope of the research work at our research center, again, so it is Center of Excellence in Functional Advanced Materials Engineering. So we focus on the full loop, right, of material development, starting from synthesis and characterizations, and then go to computational analysis and design, right, and apply that into the polymer processing, material processing and manufacturing, and try to find some application, practical application for them. And also we have a separate part of our research that focus on the use of plasma and microwave technology in enhancement of materials properties, and also in chemical recycling of materials, especially polymer, and also development of analysis devices and sensors, especially for chemical sensor. And so these are the overall scope of the research that we have conducted at our research center, or in short, we call COE FAME, right? And the main theme of the materials that we develop, right, can be classified in the group of bio-inspired materials and also functional materials. Part of them will be discussed in today's presentation. I will start with some serious problem that we have facing at this moment about antibiotic pollution, especially in water resources. Right? So we see that this type of problem about the contamination of antibiotic drug into the water resource is getting serious in the recent maybe decades. Right? So it is expected that by 2050, like 10 million deaths will be the consequence from this serious problem. Right? And many countries have some practice or some guideline or policy to deal with this. And also in terms of technical solution to this problem, right? Developing absorbent materials that can solve this problem or can eliminate the contamination of this species in the water should be very helpful. So in our lab, we have developed a type of materials that is called magnetic framework composite, or MFC here. So from last lecture, I touched a little bit on metal organic framework, or MOF, right? So in this type of materials, right, we combine magnetic nanoparticle, or MNP, with MOF, and as a result, we will have what we call MFC here, magnetic framework composite. So by combining these two type of material together, it can provide like much more advantages over using them separately. So the idea is here. So we prepare magnetic nanoparticles, and use this as core materials, and then grow a structure of metal organic framework, or frame, right, on the surface of this magnetic nanoparticle, or MNP. So as a result, the material will provide many advantages, and it can be used in various applications. For example, they will have improved, right, in terms of absorption or adsorption capacity, right, because the MOF, right, on the surface here has very good absorption or adsorption capacity. And also transition metals ion can be embedded into the shell structure of MOF right here. And also the unique property in here is when we employ MNP as core materials, right, this magnetic nanoparticle can be heated, right, by a very unique way that we call non-contact magnetic induction heating. So this is very helpful in regeneration, or improve the performance of the materials, right? And we know that already MOF has a porous structure, and also it provides possibility of further surface modifications, right? And the unique property, another unique property of NMP is also the ability to separate them, right, by using external magnetic field, or we call magnetic separations. So these are all the advantages that we can obtain from developing this type of materials. So the example that of the material that we develop here is based on Mu-53 aluminum. So we synthesize magnetic nanoparticles, right, as a core, and then in order for to grow MOF, right, on the surface of this, we just apply polyethylene glycols, right, to work as stabilizing layer on the surface, and also as a template, right, for growing MOF on the surface. So this picture, this is SEM and TEM picture of the MNP alone, and then after stabilizing by PEG or PEG, right, we can see some pattern of sponge, right, layer on the surface of the NMP. And after that, we grow, right, Mu-53 on the surface, and we clearly now see stacking pattern of MOF on the surface of the materials, right? After that, so we just characterize the properties of these synthesized materials, right, in terms of the surface area, right, micropore area, micropore volume, right, in comparison between the bare magnetic nanoparticles and the one after stabilized by after coating by MOF, and the MOF alone, right? So we see a combination between the properties of the NMP and the Mu-53 MOF, and also to verify the structure of the material that we obtain. So we use XRD. In this case, you can see that the bottom one here is the XRD trace of MNP alone, and then Mu-53, right, in a separate form. And after combining them together, so we have the top spectra here. which clearly show the peak characteristic of both components, right? So this confirmed the successful fabrication of these materials. The materials show very good magnetic properties, right? From the VSM result right here. So the MNP stabilized by PEG, right, can show very high magnetizations, right? But by incorporation of the mu53, right, the magnetizations decrease because of the dilution, right, from MOF, mu53, which does not have magnetic properties. But we look at the pattern here, right, all of them still show super paramagnetic properties. And also, we apply this in the absorption of antibiotic drug in contaminated in water. And after regeneration, we also by heating, like using induction system, the super paramagnetic property is still retained after regeneration as well. I will talk about the regeneration step here later on. And also, right, to verify the composition of the materials and also the heat stability of the materials, right, we use TGA to verify that. And also this confirm, right, the successful fabrication of the proposed materials, right, the proposed structure that we designed from the beginning. In terms of chemical structure, right, we use FTIR spectroscopy to look at the spectra of the materials, right? This is the bottom one is PEG, and then here is magnetic nanoparticle alone, and then the one when we combine them together, right? So we see clear pattern of PEG coated on the surface of magnetic nanoparticle on the top spectrum. And after that, when we incorporate, right, mu53 on the surface of the magnetic nanoparticles, we can clearly see that the characteristic peak of mu53 show up on the composite materials that we prepare. Right? This confirms that we have a high coverage of the mu53 on the surface of the magnetic nanoparticles. Now, to verify, right, the proposed application of these materials, we examine the absorption efficiency of these materials by using a drug model, right, oxytetracycline or OTC. In this case, this is the structure of the drug, right, in water, and then we measure the absorption capacity as a function of the pH of the water. And you can see here the absorption capacity is quite low at low pH, right? pH 2, pH 4, and pH 6. However, we see a drastic increase in the absorption capacity at pH 8, right, to around 200 milligram per gram of the materials, right? And high efficiency or capacity here is also observed at pH around 10 as well, right? However, if we increase the pH to 15, we see a big drop again to almost 10 or 15 milligram per gram. Right? So we also need to explain the mechanism that happen, right, that affect to this absorption efficiency. So if we look at the structure of OTC, right, there are three groups of functional group in this structure, right, that may strongly affect the performance of the absorption of our materials, right? So at low pH here, this group will be protonated, right? And the OH group and here remain no charge, right? So in this pH range. However, when we increase the pH, right, higher than the pKa of the groups, so we will see the deprotonated, right, of some OH group that generate negative charge in the structure, right? So how to confirm this? Right? We use theta, we measure theta potential of the system, and we can see that in this pH range, the theta potential remain positive, right, around 35. However, when we increase the pH, right, to around 8, right, we can see now the theta potential start to decrease and become negative, right? So this is because we convert some of the negative the active species here into negative charge, right, but at a high pH range. So from this structure change, we can divide this into 3 regions: the green region, blue region, and red region, right, which correspond to the difference in absorption capacity of these materials. Right? However, if we go to very high pH, like pH 12, this may destroy the structure of the moth, and that lead to a very sudden drop in the capacity of the absorption. Right? So from this study, you can see that we try to identify the effect or the factor that have strong effect to the absorption capacity, and also this can explain the absorption mechanism of the material as well. In terms of absorption, isotherm, and kinetics, so we look at this kinetic study and also try to fit into the isotherm different models. And as a result, we see that the maximum absorption capacity of this drug, OTC drug, on the nano sorbent that we developed is around close to 800 milligram per gram, very high number. Now, if we want now discuss the ability, right, the very unique property of this material is the ability to regenerate this by heating, right, especially by non-contact heating. So we introduce induction heating system, right? So this induction system will induce, right, magnetic nanoparticle at the core and make this magnetic nanoparticle increase in the temperature, right? Actually, the temperature here can go very high, but it also, right, will affect the surrounding area, right? So from our experiment in water system, right, it can heat up the water to around 70 degrees Celsius, right, in less than 10 seconds. Right? So this is very fast. And so we can apply this technique in the regeneration of the material after absorption of the OTC drug, right? So now we can repeat, right, doing the absorption and desorption in many cycles. And you can see that here the absorption capacity, right, is shown in the blue graph here, and also the percentage of OTC removal. During the first 5 cycles here, right, we can see that the values are almost unchanged, right? So this indicate that the material is very stable, right? By heating to 700 degrees Celsius, the structure is still intact, right? However, we start to see a decrease, right, in the number from the regeneration at number 5 and so on, right? So, but only 5 cycles here, right, can be a very promising potential of these materials. So that is the first part that I want to share. And the second part, now we will move on to another applications, right? Which is very important in industry. So in the water cooling system, right? So in many production plants and also power plants, right? Water cooling system is the essential station in the process. Right? This is used in order to to exchange heat that are generated in the plant. Right? However, because of the use of water and then which are in contact with heat here, water can evaporate and then make the concentration of dissolved species in the system, right? Have higher concentration and then precipitate. This bring up to very serious problem of scaling formation in the system. And there are many mechanisms of scaling formation in this type of system. Therefore, to prevent this, we need to do many steps in water purification or water treatments that we use them in this type of system. And each step of treatment of the water here costs a lot of money. Therefore, right, the use of anti-scalant is also very, very important in this type of operations. And these are some information about the market of anti-scalant, like global market. It is expected that it will cost around to almost $3 billion in value, right, by 2020. However, the majority of the anti-scalants that are used commercially now are usually made from fossil-based polymers, which can cause a problem to water resources when we discharge the water from cooling system to natural water resources. So these are the the overview of the formation mechanism of scale, right? The majority of scale, right, is derived from calcium cations, right, in the form of calcium carbonate, calcium sulfate. So when the concentration of calcium in the system getting higher, right, it can form start to form microcrystal, right, in small scale, right, and then they accumulate together and forming a bigger size and become a scale built up in the system, right? So if we add anti-scalant into the water, right, the anti-scalant are usually made from polymer molecule with negative charge, right? So this can absorb on the surface of the microcrystal that can prevent, right, or inhibit the accumulation of this microcrystal, right, to form scale. In some in a different mechanism, right, some anti-scalant can also have high amount of charge in the structure, and after absorbed on the surface of the microcrystal, and this can still retain the ability to disperse in the water system, right? So this is also can prevent the buildup of scale as well. So if we look at the anti-scalant that are available in the market, right, we can classify them into the group of phosphonate, right, or polyphosphate structure, and also polycarboxylate structure, right? All of these have negative charge, right? Functional group with negative charge in their structure. For the polycarboxylate, right, the common one are polyacrylic acid or polymaleic acid, right? And it should be more environmental friendly if we can develop a new type of anti-scalant that come from bio-based, and also can be degradable after use. So from this information, so we develop materials that based on magnetic nanoparticle as well, but coated by polymer structure that have negative charge. So the polymer that have negative charge here now can be behave as anti-scalant, inhibiting the formation of the scale. But we also incorporate this with magnetic nanoparticles, right? So as a result, the materials here can be dispersed in the water system and perform their function. And at the end, we can collect this back by using external magnetic field, right, to collect them back and regenerate them and reuse them, right, for more than one cycle. Right? So by using this concept, right, we can make use of the materials, right, in a more efficient way, and also reduce the amount of synthetic polymer discharge into the water resources. Right? So in this case, I'll show the materials that are made from polystyrene rock copolymer, right, with polyacrylic acid, right? And then we coat this, right, as a shell layer, right, that consists of small MNP, right, inside the particle. So we call this magnetic polymeric nanoparticles. So in the synthesis of these materials, right, we also study the effect of type of organic solvent, right, of the magnetic nanoparticle in the beginning step, right, using different type of solvent, THF, for example, and styrene. And we found out that the styrene here can be the effective one. And also we study or vary the content, right, the composition of the rock copolymer, right, per the weight of the magnetic nanoparticles, right? So starting from 0.1 weight percent, 0.5, and 1%. And we then came out with optimum condition, right, to have well-defined material, well-defined structure materials, right? Particles that consist of small magnetic particle inside, coated by the rock copolymers. So the resulting material that we have here has spherical structure, right, with homogeneous distribution of size and hydrodynamic size around 300 nanometer. Right? We use TGA to determine the magnetic particle content in the materials. It is about 70%. Right? Use theta, measure the theta potential of the materials. So this show as a function of pH. Right? So this show negative theta potential at pH starting from around 4, right, until 12, which cover the common pH range that apply in normal water cooling system, right? And also the material shows super paramagnetic behavior as well. So after that, right, we measure the performance of these materials, right? The first one here, we apply in the absorption of metal ions, and we choose calcium ion as a representative here. So the rock copolymer have carboxylate groups, right, that can bind with calcium cation in the water system. So and then we measure the absorption capacity of this. Right? So this is the absorption capacity, almost about 90%, right? And also because this material, right, consists of magnetic nanoparticle inside, therefore, after dispersing this into the water system, right, and then we can apply external magnetic field, right, to collect this material back, right? So around 5 minutes, right, 90% of the particle can be collected, right? If we wait longer to around 10 minutes, we can almost completely recover all of the magnetic particles, right, back. And after that, we can regenerate, right? We can wash out the absorbed calcium here by adjusting the pH, right? Washing with water at pH 2, so we can remove the calcium, and then this can be reused again. So this is the result from the regeneration. So you can see that the absorption capacity, right, in the first cycle is around 90% and slightly drop, right, for at least 4 cycles of applications. And so we also apply this, right, as anti-scalant and compare the ability to inhibit, right, calcium carbonate scale, right, in comparison with other commercial anti-scalant, for example, PBTC, PMA, Akuma, right, in the market, right? And this is our material right here. You can see that the inhibition efficiency of our developed materials, right, is in the same, right, range of those available in the market, right? But the unique characteristic of our material is they can be reused, right, for several cycles. So that is the second part, right? The third part now, I will move on to the development of chitosan derivative and their application in water treatments and also water filtrations. So everyone probably know chitosan already. This is bio-based polymer and biodegradable as well. That can be obtained from crustaceous animal, right? For example, shrimp or crab shell. And then if we extract this, right, we can have the polymer in a form that we call chitin right here. And if we deacetylate, right, this acetyl group right here, and this can be converted into chitosan, right? And the structure of chitin and chitosan here can be modified in many ways, right? And to add special function to these materials. For example, we can make them have positive charge, right? So we call this quaternized chitosans, right? Or we can make them convert the OH group to be carboxylic acid groups, right, by oxidation reaction, for example. And also we can modify the structure, right, to have both positive and negative charge in the structure. That is called polyampholyte structure. Chitosan, right, that are quaternized, right, or we call quaternized chitosan. So we include ammonium, right, with positive charge into the structure of chitosan here. Right? It's very well known that it shows very high antibacterial activity. Right? So one of the promising synthesis of this type of quaternized chitosan is reacting chitosan with glycidyl trimethyl ammonium chloride, or GTMAC. Right? For the oxidation of a functional group in chitosan structure, right, we can convert the OH group, right, OH group in chitosan structure, right, hydroxyl, into carboxylic acid group, right, that can also generate negative charge carboxylate later on. One of the promising process, right, for doing this is oxidizing by tempo, right? And tempo here is very effective oxidant for chitosan structure. But the use of tempo in this reaction usually require co-oxidant, right, that contain halogen atoms like bromines or chlorine, right? This still, right, raise concern about environmental concern as well, right? If we discharge this into the water system, right? Even though this system is very promising because they are highly selective, and also it only oxidize the OH group, but do not break down the chain of the chitosan, right? This is the unique property of the tempo system. However, right, the main drawback here is it requires halogen compound, which is not quite good. In our lab, so we develop a halogen-free, right, green and mild process, right, to generate the oxidant species, right, from tempo, right, by without the use of halogen compounds. So in this case, we use ozone as co-oxidant instead. So this process, right, can occur at very mild condition at low temperature, and also at the same time we develop a characterization technique that are fast enough to monitor the progress of this reaction, and the resulting tempo plus, right, that are generated, right, are very stable, right, in dilute acid solution at low temperature, right? We can keep this for like almost at least 1 month, and after that this can be applied, right, in the oxidation of chitosan structure, right, to generate what we call chitosan polyamphorite. So how can we make chitosan polyamphorite that contain both positive and negative charge in the structure? First, we need to generate quaternized chitosan or QC. So we incorporate positive charge into the structure of the chitosan, right, by reacting it with GTMAC, right? So by doing this, we can increase the solubility of the chitosan, right? The chitosan, the QC materials here can easily dissolve in water, right? So we can vary the degree of quaternization, right, starting from 10%, right, until very, very high. The percentage here is counted per one OH group or one NH group, right? So this is higher than 100 because there are two possibilities that this can react, right? So, and we confirm this by standard characterization technique using NMR and FTIR spectroscopy, right, to quantitatively look at the structure of the resulting QC here. And after that, we use the QC, right, in the oxidation reaction by the oxoammonium solution that we, or tempo plus that we already prepare, right? So by doing that, we change the OH group at this position into carboxylic acid, right? And also carboxylate here. So as a result, the final polymer here is called chitosan polyamphorite or CPA that contain both positive and negative charge in the structure, right? We can vary the degree of oxidation here, right, from 70% or until complete oxidation of the OH group 100%. It is very interesting because this structure here, right, consists of both negative and positive charge. So if we just do not do anything to this, right, they form what we call self-folding structure and become nanoparticles by themselves, right, because of the interaction between the negative charge and positive charge in the chain, right? However, we also find a way to make this unfold and then and then can be in the form of stretch chain, right? And dispersed in water system. And we confirm that by TEM and also SEM and EDX characterization, and also measuring the size of the self-folding structure of this CPA as well. We then apply this as anti-scalant compound in water cooling system. And in this case, we use the synthetic calcium solution with 220 ppm, right? And compare the inhibition efficiency of our material CPA here with commercial anti-scalant that are used commercially. You can see here with the same concentration of the anti-scalant, right, the performance of CPA, right, is even higher than commercial fossil-based anti-scalant in the market. And also we look at the effect of the concentration of the anti-scalant as well. And also at higher concentration of calcium, right, this also still perform very well, like comparable or even higher than commercial anti-scalant as well. We also look at the inhibition mechanism, right? Because different type of anti-scalant will show different inhibitions mechanism, and we can determine this mechanism by look at the picture, right, SEM picture of the resulting microcrystallite that have been inhibited by different type of anti-scalant in here. But I will not go into the detail of this for today. The materials, right, the CPA material here also show very high antibacterial properties against both E. coli and also S. aureus bacteria. But if we compare this with QC alone, QC will show higher antibacterial, right? Because the main function, right, of antibacterial activity usually come from the positive charge, right, from the ammonium part right here. But this also show very promising potential of this application, right? Because in water cooling system, right, we need to apply anti-scalant and also antibacterial or anti-fungal at the same time in the same system, right? But this material can show both activity, right, in only one structure or one materials. So those are the third part, right, that of the materials that we developed. And the last part right here, and I will share with everyone, right, is concerned with the chitosan-based composite membrane. This is our collaborative work with Professor Fitri and the team at UPI. So in this study, we make chitosan-based composite membrane, right, by using chitosan, polyethylene glycol, PEG, and add a multi-wall carbon nanotube, right, into the structure, right, and also apply benzalkonium chloride or BKC as antibacterial agent into the system, right. So we vary, right, the concentration of BKC in the structure, and then we observe the porous structure of the membrane, right. We can see that at low concentration of BKC, right, we can the pore structure here seem to be spherical shape, right. However, if we increase the concentration of BKC more and more, you can see that the pore structure is like a distorted structure or stretched pore, right. So we try to explain what is going on, right? What is the origin of this structure formation? So we come up with the proposed structure like this. So when we add BKC, right, in the structure, this have planar benzene ring, right, that can stack together or stack with multi-wall carbon nanotube, right? And then make this positive charge, right, ammonium group, right, pointing out, and then covered by PEG. And this PEG make them more compatible with the hydrophilic chitosan structure, right? So as a result, when this structure is formed, we can see that this is elongated or oval structure that are similar to what we see in the structure of the membrane, right? So this is the proposed structure that we obtain, right, from intensive characterization of the properties of this material by different techniques like FTIR spectroscopy, XRD, and SEM. And as a result of this structure formation here, we have stack of benzene ring that can make pi-pi interaction between them, and also a very strong chart, right? Chart and pi interaction or hydrogen bonding between the structure. As a result of this, we see a big improvement or enhancement in mechanical properties of the membrane. So this is a stress strain curve of the membrane that containing different amount of BKC in the structure, starting from 0, right? A right here, you can see this can break early, right? Low elongation. However, when we increase more and more BKC in the structure, we see increase in elongation, right, or toughness of the membrane. And in terms of the surface hydrophilicity, right, we see an increase, right, in the water contact angle, right, indicating more hydrophobicity of the surface, right, as a result of the benzene ring of the BKC structure. And this also show, right, very good antibacterial properties, right? So with the increase of the concentration of the BKC in the structure, right, we see higher bacterial killing ratio, right, against both E. coli and S. aureus bacteria. And also we study the performance, right, of this membrane in terms of the flux and also the rejection percentage using BSA and also azo blue dye in the measurements. So we see that the increase in the BKC content, right, make them more hydrophobic, and this flux decrease as a function of BKC in the membrane. So those are all the four, right, the four functional material systems that are applied in the field of water treatment and water purifications. And to summarize this, we can say that MFC nanoparticle has been developed and used as absorbent, effective absorbent for antibiotic pollutions, right? And also magnetic polymeric nanoparticles have been synthesized for use as metal ion absorption, and we show the absorption against calcium ion, and also this can be used as reusable anti-scalant, right, for many cycles. And to be even more friendly to the environment, right, we modify structure of chitosan and to become chitosan polyimpholite that contain both positive and negative charge. And this can be employed effectively as anti-scalant, right, that come from bio-based and friendly to the environment, right? And the last part, I touch on the development of chitosan-based composite membrane, right, that show enhancement in the toughness, right, of the membrane, and also show antimicrobial properties, right? And also this has high potential, right, for use in water filtration, right? And if you want to look in more detail about this work that I share with everyone today, these are the list of the paper that we have published on this topic, right? So you can look in more detail. And finally, I would like to thank or express our sincere gratitude to all of the granting agency, right, who give us the support that make this work possible, especially to the Electrical Generating Authority of Thailand, or EGAT, right, who support us on the anti-scalant development. And also this work, right, conducted mainly by 3 or 4 key persons here. The lady right here, Dr. Chariya, right? Our a PhD student in our lab, Tilina, right here, and a PhD student of mine who already graduated now and is postdoc in UAE already, Dr. Dufam, right here, and also Professor Fitri, right? So again, thank you very much for your kind attention. And if you have any questions, we can discuss this at the end of the presentation from other 2 speakers. So thank you very much.
All right, thank you very much, Prof. Pakon, for excellent talk. So you share with us several interesting materials, yeah, and system for various applications. I note here, firstly, you introduced to us about the magnetic framework composite, yeah, that you prepare from the MOF and magnetic nanoparticle, which is, in my opinion, it's really wonderful, yeah, with really great properties. I even observed the really huge surface area for your system, yeah, for absorptions applications, and also the good thermal stability, as well as other magnetic excellent magnetic properties. And other thing also you share with us about the other excellent system for magnetic polymeric particle, which is can be applicable for both purposes, not only for absorbance of metal ion, but as well for anti-scalant, yeah. Again, we here as well facing the similar serious problem regarding to the prevention of scaling, yeah, in water treatment plant especially. And another good system that also you share with us is another composite that you prepare from quaternary chitosan, as well as the oxidation chitosan, that even not only showing the anti-scalant activities, but also the good antibacterial activities. Yeah, and yeah, finally you close your presentations with our current work on development of a composite membrane. Yeah, that would be promising for the filtrations applications. Now we still in the collaborative work to finish the second draft, yeah, Prof, regarding to the applications of this composite membrane, especially in the dead end and filtrations cross flow filtration method. Thank you, Prof. I do believe all participants will keep the questions, so please kindly write down if you have any comment and suggestion for the first talk. And we would like to move firstly to the second speaker here. Before properly deliver his presentation, we would like to briefly introduce him. The second speaker is Prof. Sang Yen Lee from School of Disaster Prevention and Environmental Engineering, Department of Civil Environmental Engineering, Kyungpook National University, Korea. Yeah. And the following is his educational background. Yeah, for bachelor program, he obtained from Jeju University, Korea, in the major of environmental engineering. And for master program and PhD program, he obtained from Gwangju Institute of Science and Technology, GIST, Korea. Now, there are one student of our university, Prof, who learned in GIST for PhD program, but he joined with the laboratory, especially for anti-corrosion, if I'm not mistaken, and catalyze. Yeah, and in the Guangzhou Institute of Science and Technology, he obtained for master and PhD program in the major of environmental engineering. So yeah, he really mastery in as the environmental engineer, I guess, yeah, with the consistent educational background. And then here is the information of his professional experiences. Yeah, he has a great experience, yeah, as the postdoctoral fellows, yeah, in the postdoctoral fellows School of Sustainable Engineering and the Built Environment in Arizona State University, United States, and also she has a great experiences as the senior researcher in Department of Membrane Development of Toray Chemical Korea, and also in the Department of Environmental Machinery, Korea Institute of Machinery and Material. And then, yeah, currently, I guess this is from 2019. Yeah, he already is the assistant professor at Department of Civil Environmental Engineering, Kyungpook National University. And very interesting, he also been published a significant number of the publications for all participants who really interested in to know, yeah, his publication record. You can kindly find in the Google Scholar or Scopus, yeah, with significant age in here, and even he published 7 patents here. And for his research interest, as we obtain from his brief informations, yeah, and also some maybe would be delivered in today presentations. Yeah, he has some research focus on, I guess, pressure retarded osmosis and forward osmosis, yeah, membrane processes, and I guess some innovations, yeah, in the effect of norm of transport, yeah, in the aquatic environment. So we do believe he can share his great experiences on his research work today. And probably without any further ado, time is yours.
Hello? Okay, can you hear me well?
Sure, excellent, bro. So you
Okay.
can start. Yeah.
Thank you for kind introduction. Hello, I'm Seung-Yoon Lee from Kyungpook National University, Korea. First of all, I'd like to thank you for inviting me to this online WCP seminar. Actually, today is one of the biggest holidays in Korea, and I'm happy to celebrate this Chuseok holiday with you together through this online seminar. Okay, from now, I'd like to talk about forward osmosis membrane technology. I guess most of you are unfamiliar with the forward osmosis and membrane water treatment process. So first, I'd like to talk about a brief introduction of FO process. And then I will explain some issues to consider in FO process. And I will show you some of my research results relating to these issues. After that, I will talk about FO process design. And finally, I will show you some application field using FO process. Okay, first, let me start with the definition of membrane. Membrane can be defined as selective or semi-permeable barrier. Here, selective or semi-permeable means that it allows something to pass through, but it does not allow others to pass through the membrane. In most cases of water treatment process, the membrane selectively allow only water to pass through the membrane. And pollutants such as bacteria, virus, organic matter are removed by the membrane. And the selectivity of membrane or removal efficiencies of membrane are depending on the membrane pore size or size of the pollutants. Of course, membranes with a smaller pore size will provide better removal efficiency. As shown in this slide, the membrane can be classified depending on the pore size. The microfiltration, ultrafiltration, nanofiltration, and reverse osmosis membrane. In case of RO, as shown in here, even monovalent ions cannot pass through, and only water can pass through the membrane. Although RO, reverse osmosis membrane, provides highest removal efficiencies for these solutes, RO requires highest energy for operation because the membrane pore size is also too small for water transport. Okay, this slide shows the principle of the forward osmosis. When the two solutions with different concentration of salt are divided by the semi-permeable membrane, the water transport from feed solution, low concentration side to high concentration side. We call this phenomena as the osmosis phenomena. And however, in case of RO, hydraulic pressure higher than the osmotic pressure difference should be applied to high concentration side, and water transports from high concentration salt side to low salt concentration side. Therefore, RO requires a high energy for operation due to the hydraulic pressure. However, in case of forward osmosis, it uses high concentrated water. It's called draw solution, and it uses the osmosis phenomena to get water. So FO process does not require high energy for operation. Okay, in FO membrane process, water naturally transport from the low concentration side to high concentration side by osmosis. And the final product of the FO process is a concentrated feed solution and diluted draw solution. And due to the convective water flow, contaminants can accumulate on the membrane surface, but this fouling layer is loose compared to the fouling layer in RO process. This is because RO process are operated under high hydraulic pressure, so that the fouling layer is compact and dense, so it is difficult to remove. But in case of the fouling layer in FO system, it is loose, so it can be easily cleaned by simple physical cleaning. So this table summarizes the advantages of FO process compared to RO process. Driving force of the FO is osmotic pressure. So the energy demand is low compared to the RO system. And FO does not require the pressure. So the fouling layer is can be easily removed. In addition, in case of RO, the final product of RO is concentrate. But in case of FO, it does not have any byproduct to treat. So FO is a more environmentally friendly process. So it seems that forward osmosis process is a perfect process, but there are some considerations. One of the major issues is the draw solution recovery. This slide shows the example of FO process. Here, seawater is a feed solution, and draw solution with a high osmotic pressure is used to extract water from the seawater. And diluted draw solution goes to the draw solution recovery system. Here, the product water is produced by separating the fresh water from diluted draw solution. Because high energy is consumed in the draw solution recovery process, the whole FO process may consume higher energy compared to RO process. So there is no free lunch. For the osmosis membrane technology has gained a lot of attention in the world since 2005 due to its unique advantage. And I will study the FO's research since 2013. Although there are some technical bottlenecks, but I believe a full processor will be implemented in your future. Okay, now let's look at what we have to improve in FO technology. I think there are four parts to consider in FO process: draw solution and FO membrane, and we have to improve the FO membrane module, and we have to study relating to the FO process engineering part. Let me close look at each part. First one is the draw solution. As I explained earlier, fresh water should be separated from the diluted draw solution and in the regeneration system. And the recovery, this system may require more energy compared to RO. Therefore, for the economically feasible, the draw solution should be easily separated. And if the final product is used for the drinking water, then the toxicity of the draw solute also should be considered. And also draw solution should be chemically non-reactive with the FO membrane for long operation. Various researches have been conducted to develop new draw solute to reduce the recovered energy. Most of these draw solutes changes their physical phases or solubility depending on temperature. There are also magnetic nanoparticles as presented by the previous speaker, Professor Opara Kassit. And I think among these, the interesting draw solution is fertilizer, which doesn't require draw solution separation process. Instead, the diluted fertilizer can be directly used for agriculture. So I think that kind of FO system can be operated with a very low operating energy. Second consideration is FO membrane. At given concentration difference, theoretical osmotic pressure difference can be calculated by using the Van 't Hoff equation. However, all the osmotic pressure difference cannot be utilized due to concentration polarization inside and outside of the FO membrane. Because only water can transport through the membrane, the feed concentration will increase near the membrane active layer. And this is called external concentration polarization. And by the water flux, draw solution inside the membrane support layer will decrease. And this is called the internal concentration polarization. Because of this ECP and ICP concentration polarization, the effective osmotic pressure difference is significantly less than the bulk osmotic pressure difference. Therefore, we cannot get a high water flux. To increase the effective osmotic pressure difference, it is important to reduce ICP because ICP has greater effect than the ECP. Then how can you reduce ICP? Thin film composite for the osmosis membrane consists of 3 layers: very thin active layer, and porous support layer, and non-woven fabric backing layer. This active layer determines the solute rejection, and the internal concentration polarization is closely related to the support layer of the membrane. To minimize the internal concentration polarization and to improve the water flux, we need to reduce the solute diffusion resistance of the support layer. So we have to make a porous support layer and thinner and more with low tortuosity. In addition, to improve the water flux of the FO membrane, we need to modify the membrane to be more hydrophilic and have the high salt rejection. This slide shows the SEM image of RO and FO membranes developed in our research team. And compared to reverse osmosis membrane, forward osmosis has a much thinner thickness, and it has the finger-like structure, so it has more porous support structure inside, so the solute can be easily diffused inside the membrane, and also it has a lower tortuosity. Using this structure, we can minimize the resistance of the salt diffusion inside the membrane so that we can get a higher water flux. When we compared the water flux compared with the commercialized CTA FO membrane, our TFC FO membrane had a twice higher water flux. And in addition to the membrane module design is also very important to get a higher water flux. In case of reverse osmosis membrane module, there is just one input flow, feed solution. However, in case of the forward osmosis membrane module, there are two input flows, feed solution and flow solution. So the flow channels of the FO membrane is more complicated. This slide shows the spiral wound FO membrane module and draw solution. Draw solution flows inside the membrane envelope, and the feed solution flows outside of the membrane envelope. And these two solutions should flow very smoothly to utilize FO membrane performance. For better smooth flow, thick spacer like a net type spacer is installed inside the membrane envelope. Ideally, the FO process does not require hydraulic pressure to operate, but in rear, we need to apply some pressure, about 1 or 2 bar for water flow. And if we apply too much pressure outside of the membrane envelope, the membrane can be deformed like this, and it can block draw solution flow. And this deformation can damage the membrane, and so that the flux and the removal efficiency can be decreased. Therefore, it is important to install the optimum membrane spacer to minimize membrane deformation and to increase membrane FO module performance. We tried various types of spacer with different size and combination, and we found that the combination of the tricot type and the mesh type spacer could reduce the membrane deformation, and it provided higher water flux compared to other types of the membrane spatial condition. Last part to consider is FO process design. FO process design include finding optimum operating condition and FO process design. The main purpose of the FO process can be the main purpose of the FO process can be either the feed volume reduction or dilution of the draw solution. Therefore, the feed solution recovery is one of key performance factor. So we need to find optimum concentration of the draw solution and feed solution, and we need to find optimum velocity of draw and feed flow rate. Finding optimum the operating condition is not simple because FO performance is not linear to one parameter, and the parameters are related to each other. For example, if we change the solution concentration to change the osmotic pressure difference, then the water flux can be increased, but the increased flux can also increase the ICP effect and will hinder the increase of the water flux. And the increased or decreased feed volume or draw solution volume will affect on the operating pressure. Until now, we looked at important considerations in FO technologies. Although there are some difficulties, I believe FO process can be commercialized in near future because many companies and researchers are trying to improve FO technology in their field, including FO membranes and draw solution and engineering part. My recent research interests are in FO system engineering and application part. So from now, I'd like to talk about FO system and application part more detail. This slide shows one of the FO applications, and the purpose of this process is the wastewater volume reduction. In this application, I wanted to answer how many membranes is required and how to operate this system and what draw solution concentration we need for target feed concentration and volume rejection factor and amount. To answer this question, I use the experimental data and modeling, and I try to suggest the key design parameter. For this study, I used plate and frame FO membrane module from Peripheral instead of the spiral wound FO module, because this plate and frame module has a lower flow resistance in both feed flow and draw flow channel, so that it has more advantage in large scale design compared to spiral wound FO module. Let's look at mass transport in FO membrane module. In FO membrane module, the water moves from feed solution side to the draw solution side, and the feed concentration increases and draw concentration decreases around the membrane module. Using the water flux, we can calculate water recovery, and which is the key FO performance in this study. And Deshmukh suggested the equation to calculate theoretical water recovery and required draw solution concentration as function of the feed flow rate fraction and the concentration of draw solution, concentration of feed solution, and membrane properties. These equations assume that the feed and draw solution reaches equilibrium at the exit of the membrane module, And I validated this equation by experiment and tried to suggest a process design parameter. Membrane characteristics A, B, and S values were measured using the bench scale test, and I used these values for modeling. This slide shows the example of theoretical water recovery estimation as a function of the feed flow rate fraction. And as we expected, the water recovery estimated increased as increasing draw solution concentration and decreasing the feed concentration. And both graphs shows that the water recovery decreases dramatically when the feed flow rate fraction is over than 0.8, and therefore the practical feed flow rate fraction is between the 0.5 and 0.8. This slide shows the pilot scale experimental setup for this study. Its membrane module has 1, 3, and 6 FO elements, and these modules were operated individually or together, connected in series by adjusting the valves. Therefore, we could investigate the effect of the membrane area on FO system. We changed various operating conditions, including the flow rates and feed and draw concentration and membrane area and flow rates. And we observed the effects on the permeate flux and water recovery and concentration at the exit of this system. And we also monitored the pressure change. For example, when we increase the membrane area, the total permeate, water permeate, and water recovery gradually increased. And as increasing membrane area, the concentration of the feed and the draw solution at the exit of the membrane module approaches to the equilibrium. This slide shows the effect of the operating condition on water recovery at different membrane area. This blue line represents the theoretical maximum water recovery as a function of the feed flow rate fraction, and the pink area represents where the water recovery is higher than 0.5, and the feed flow rate fraction is between 0.5 and 0.8. When we used the 7 square meter membrane area, the obtained water recovery is far less than the theoretical value. And when we increased the membrane area, the recovery value approached to the theoretical value. So this slide shows the importance of the membrane area to estimate the water recovery performance. And we conducted a FO test under various feed and draw solution concentrations and using different number of the membrane elements. And this graph shows that the comparison between the theoretical water recovery and the experimentally obtained water recovery. And this solid line represents one-to-one line. As shown here, there was an interesting trend that all the results approach to the one-to-one line as increasing the number of the membrane modules or the membrane area. We plotted the same result as a function of the normalized membrane area and the water recovery ratio. Here, normalized the membrane area means membrane area divided by the feed flow rate, and the water recovery ratio represent the ratio of experimentally obtained water recovery to the theoretical maximum water recovery value. So as you can see here, there was some relationship between these two values. For example, when we design a process using the normalized membrane area at 0.08, the Apple processor will provide water recovery around 80% of the theoretical maximum value. This slide shows the example of the Apple process design using our previous graph. If we know the target condition, the feed concentration, and the amount we have to treat, and if we know the target recovery value, and if we select normalize the membrane area of the 0.08, then we can expect water recovery performance of the system, and therefore we can use using the normalized membrane area, we can calculate how many membrane area we have to use, and required draw solution concentration can be calculated using the decimal equation. So as I explained, we suggested normalized membrane area as a key parameter for the Apple process design. Finally, I'd like to share some of the Apple application field. As I explained, the Apple process can be used for either the concentration of the solution or the dilution of the draw solution. So as explained, draw solution recovery can require a lot of energy. So I think the application field which does not require draw solution recovery will be the best application for the FO process. And one of that kind of the FO process application is a fertilizer drone for the osmosis system. Using the fertilizer as a draw solution, this process can extract water from the saline water, and the diluted fertilizer can be used for the fertigation. So we can save the fresh water for the agriculture, and we can save the energy to extract water from the saline water. And the similar concept can be used for the microalgae harvesting. Using the fertilizer as a draw solution, we can concentrate the microalgae, and the final product, the concentrated microalgae, can be used for the biofuel resource or the food product. And the F4 system can be used for the seawater desalination. In this process, seawater is used as a draw solution, and the treated wastewater effluent is used for the feed solution. So in this process, the water can be extracted from the wastewater, and the final product is diluted seawater. And we can reduce the desalination energy in our process using this diluted seawater as a feed solution. Okay, these are all I prepared for today, and thank you for listening. Thank you.
All right, thank you, Prof. Lee. Very interesting. Yeah, thank you for your outstanding talk. It's quite new for me. Yeah, for the chemist, since maybe your background is more dominant in the engineering aspect. But anyhow, today we obtained really great information. So in the beginning, you try to describe about the forward osmosis process, yeah, and then you contrast between the reverse osmosis. Mostly for chemists, maybe we really, how to say, well known with reverse osmosis rather than forward osmosis. But today, yeah, thank you for your great sharing. We obtained the new knowledge about the benefit, yeah, of the forward osmosis. And actually, the forward osmosis and reverse osmosis, how to say, have the different advantages and also disadvantages in terms of driving force, as well as energy consumption and the potential for membrane pulling, and also for the environmental effect. And probably also share with us about the thing that need to be considered one time we conduct the process, yeah, with the forward osmosis. Firstly, we have to consider about the drought solutions, and then secondly, we have to consider about the forward osmosis membrane itself. I still have some question here later on, maybe in the Q&A, very interesting. And then thirdly, about the forward osmosis membrane module itself, yeah, and the FO processing engineering. And by the end of the presentations, yeah, thank you very much for your great sharing as well about the applications, yeah. So far we know it's only for water, but from your presentation, even it can be applicable, yeah, for agricultures and so on, in terms of how to say concentrations application or dilution concentrations. So I do believe not only myself, but as well the participant maybe still keep the questions or comment regarding to your presentation. So to all my beloved participants, please kindly wait, yeah, for the Q&A session. And actually from now on, you can write down your questions through the chat room, yeah, so all invited speaker can catch your questions, yeah, from now on. And let's try to move to the third speaker. Very glad for me and to introduce our third speaker. Actually, I never been met with Pak Lubis, but through my connections in Indonesia Institute of Science, now it changed become BRIN, yeah, my former colleagues, yeah. Finally, I can meet you virtually, Pak Adli here. So here is our third speaker, Bapak Muhammad Adli R. Lubis, PhD. Now currently he's working as a researcher at a research center for biomaterials of National Research and Innovation Agency, formerly it named as Indonesian Institute of Science. And here is his following educational background. Yeah, for bachelor program, he obtained from Institute Pertanian Bogor. Now it's well known as IPB University. Yeah, very close to Jakarta and also to Bandung. And for the PhD degree, he obtained from Kungpok National University. Very coincident, yeah, at the same institution. With probably later on, maybe we can have formal and informal discussion together in the field of wood science and technology. And yeah, currently he keep the research focus on wood adhesive, wood-based panel, and also forest product technology, and as well the polymeric resin. And next, yeah, he has also great concern not only in the how to say routine research, but as well some. I guess this is the a very special scheme, yeah, for research for the university. I'm not sure we have the special how to say promising grant like this, but for research in the categories of industrial based research and the government based research. So far, yeah, very consistent. He's still working with the wood composite, wood adhesive, and also food packaging. I guess it's very close to our daily life. So I do believe, yeah, by following your presentations, yeah, later on, yeah, we can understand the wood processing technology, yeah, have been done so far in our country. So, Pak Adli, Ovalubis, without any further ado, time is yours.
Okay, thank you very much, Dr. Fitri, for the kind introduction. Can you hear my voice clearly? Can you hear my voice?
Yes, Doctor.
Okay. thank you very
Yeah,
much.
excellent. Excellent, Pak Lubis.
Okay. Hi, Professor Pakon. Hi, Professor Lee. 안녕하십니까? 반갑습니다. Thank you very much for the committee for inviting me to this seminar series in polymer composite science and technology. So I'm Muhammad Adi Lubis from Research Center for Biomaterials, National Research and Innovation Agency, or BRIN. So today I would like to share my knowledge on high performance bio-based and ultra low emission of adhesives for wood-based composites. So this is the outline of the today presentation. I will talk a bit of the wood adhesives and then wood-based composites, and then ultra low molar ratio urea formaldehyde resins, and then the influence of the initial molar ratio, intercalation of nanoparticle, and then bio-based adhesive based on the oxidized starch, and also natural rubber latex. And finally, I will talk the summary of this presentation. So, Research Center for Biomaterials, National Research and Innovation Agency. This is my office. It was established in 1983. It is a government research institute. It is a center of excellence in biomaterials in Indonesia. It's located in Cibinong, West Java. To support our research activity, we have integrated laboratory of bioproducts. We call it iLab. So in here, we do develop bio-based materials from biocomposite, bioadhesive, biopesticide to biomaterial for medical devices, and also bioactive materials such as bioactive for bioremediation and nutrition, and also transport of active materials. So we do also provide services for characterization, identification, quantification, and then processing, formulation, methods, standardization. So to support our services, we are equipped with the everything coupled with EDS, microconfocal Raman, until molecular equipment such as PCR. So talking about wood adhesives, I think it's totally different from Professor Pakon and also Professor Lee. So we will talk a bit of wood adhesive. Wood adhesive market reached 16.2 billion in 2020, where Asia is the biggest market, reaching 5.3 billion, and then followed by the Europe and the Middle East, and then America. Among the wood adhesives, urea formaldehyde, melamine formaldehyde, and phenol formaldehyde are the main wood adhesive used in the manufacture of wood-based composites. And then followed by the isocyanate and its derivatives, such as PMDI, and also polyurethane resins. And then the last, some of bio-based composite use wood-based composite use bio-based adhesives such as latex, lignin, tannin, organic acid, protein, and also carbohydrates. So why wood adhesives? Adhesives are the most social of polymer products we use. They exist for the purpose of bringing other materials together. So based on the history, phenol formaldehyde is the great-grandfather of wood adhesive. It was found in 1900s, and then followed the polyphenol acetate, urea formaldehyde, and then isocyanate during the World War, and then starch, and dextrin, tars, and protein, epoxy resin, and then there's a melamine formaldehyde, and the new one is the one-component polyurethane resins. So these are the typical wood adhesive we use today. There is a urea formaldehyde with a milky colors and then transparent color of melamine formaldehyde, a black color of phenol formaldehyde, and then we have also polyphenol acetate, two-component epoxy resin, isocyanate, polycarboxylic acid, lignin and tannin base, polysaccharide base, and also natural rubber latex base. So in Indonesia, we have some companies focused in production of wood adhesive. The biggest one is a palmolid adhesive in Probolinggo, and then followed by the Dover Camp. We also have a Glora Citra Kimia Abadi. And then for the global wood adhesive company, it's Hexion in United States, and then Georgia Pacific in United States, and BASF in Germany, and many international wood adhesive. So these wood adhesive are used in the manufacturing of wood-based composite. So we need to know what is the wood-based composite in here. So in here we can see that there is raw materials, processing, density of which determine the wood adhesive, wood-based composite production in here. When we use raw materials such as fibers, and then we can produce fiberboards such as low density fiberboard, medium density fiberboard, and high density fiberboard, and also paper. These products are produced using a wet processing. And then for the fiberboard, there is a dry fiberboards that use a less amount of water. It is a medium density fiberboard and also high density fiberboards. When we use particles as raw materials, and then we will produce particle board, flake board, stern board, and also wafer board. All these particles types of products, they use dry process. When we use veneer, and then we will produce plywood, and then we use lumber, and then we use glue lumber or glue laminated lumber or timber. And the new one is the cross laminated timber. So this wood-based composite has a variety of density and also specific gravity, which some of them can meet can be to replace the solid wood in here between 0.4 until 0.8 specific gravity of all density. So it is so potential to use wood-based composite as a replacement of solid wood. As we know, we face deforestation. It's really difficult to get a good quality of solid wood. So this is a trend of plywood production and consumption in Indonesia and global. So we are one of the biggest plywood production in the world. And then for the particle board also, and for fiberboard also. Three of this wood-based composite, plywood, particle board, and also fiberboard, they are used for furniture materials, mostly for interior application. They are produced using urea formaldehyde resin. Why urea formaldehyde resin? Because it's the cheapest wood adhesive in the world. Almost 90% of the wood-based composite are produced using urea formaldehyde. So we need to meet the customer expectation, not only to provide better materials, but we need to develop low emission of wood-based composite, and then sustainable, and also high performance in high humidity. So in order to answer that, we developed the ultra low emission adhesives in here. So it's based on the urea formaldehyde resin. As I said, it is really cheap, inexpensive, and then it has fast curing rate. It has good performance and also colorless after hot pressing. But it has several disadvantages, such as a lower water resistance. It emits formaldehyde, low durability, and only used for interior application. So the main problem here is the formaldehyde emission due to low water resistance. So we can reduce the formaldehyde emission by controlling the synthesis and formulation, and then lowering the formaldehyde to urea mole ratio, and then we can add scavengers such as a urea solution, and then do the post-treatment. But usually, the first and second method is more preferable because it's much more cheaper compared adding some additives such as scavenger or post-treatment into the UF resin. So this is a typical synthesis of UF resin. To prepare UF resin, it is usually using the addition and condensation reaction. So first step is the addition. It is usually occur at alkaline pH around A, and then at that condition there will be addition or methylation reaction where the urea will react with formaldehyde and then form mono D and 3-hydroxymethyl urea. And after that, when we reduce the pH to acidic pH, and there will be condensation reaction, and these oligomers will react each other and then form bigger molecules such as a methylene diurea and hydroxymethyl methylene diurea. So first, there is an influence of initial formaldehyde to urea mole ratio. So in here we study the influence of the first initial and second initial mole ratio to the properties of urea formaldehyde acid. So we provide three different mole ratio of first initial mole ratio and two different types of initial mole ratio in here. So we can see in here that not much different in non-volatile solids content, viscosity, and also specific gravity and pH of the UF resin produced from these methods. But the second method, which produced by combining the first initial molar ratio with second initial molar ratio of 1.7, it produced shorter gelation time. That means it has faster curing compared to the first methods, and also it has less free formaldehyde in the UF resin. So when we check the molecular weight distribution of the UF resin using GPC, the first method has produced more low molecular weight fraction compared to the second method. So in here, the distribution is the molecular weight is around 4 to 5 gram per mole until 677 gram per mole for the first methods, and then it's a bit higher for the second method from 484 gram per mole until 696 gram per mole for the second method, and we can see more high molecular weight fraction in here. And then when we check using XRD, the crystallinity patterns change. And then the crystallinity reduce when we prepare UF resin using the second methods. So the crystallinity reduced to the 45.2% by using a 4.0 FO ratio and 1.7 initial FO ratio. And then when we check using the differential scan calorimetry, we can get the curing temperature of the adhesives. So the first method, it has a curing temperature around 95 degrees Celsius to 120 degrees Celsius. Depends on the combination of first initial mole ratio and second initial mole ratio. But the second method, it produced lower curing temperature. It reached 75 degrees Celsius, the lowest one. And the highest one is around 120. So this results show that the UF resin prepared using second method, combination of the first initial mole ratio and second initial mole ratio of 1.7, produce better properties of urea formaldehyde resin. When we applied the adhesive in plywood, so we can get the best result at combination of 4.0 first initial mole ratio with 1.7 second initial mole ratio with tensile shear strength of 1.21 megapascal and formaldehyde emission of 0.55 milligram per liter. So what happened in the plywood, when we check under microscope, we can get this is the plywood entering the wood cells, and this is the empty wood cells in here. So we can calculate the bond line thickness of the adhesive in the plywood layers, and also the resin penetration. So how that the resin goes into the wood cell. So we can calculate. So we don't want the adhesive do over penetration into the wood cells. And also we don't want the adhesive stay in the bond line. So we need the proper combination of synthesis and formulation to produce a balanced bond line and resin penetration of adhesive. And finally, it can produce high tensile strength and low formaldehyde emission of plywood panel. So after that, we do the intercalation of nanoparticle in low molar ratio UF resin. And here we use a nanoclay. So before you do the modification, we do the intercalation of nanoclay in UF resin. We did modification of nanoclay using ion etching method, using transition metal ions, and also octadiesel amine in here. For the transition metal ion, we use copper chloride. For the another one, we use the octadiesel amine. So after the modification, we add the modified nanoclay during the synthesis of UV resin. We call it in situ modification. So during the addition reaction or methylation at pH 8, we add the nanoclay at different levels, and after we reduce the pH, and then it would go to condensation reaction. And at this time, the nanoclay will intercalate or partially exfoliate in the UF resin polymers. So this will enhance the adhesion performance and reduce the formaldehyde emission of UF resin. So what happened after the modification? The nanoclay, first the nanoclay, the pristine or the net nanoclay, the original nanoclay, it has we use bentonite in here. It has a diffraction angle around 7.5 to 7.7. And then after the modification, either using the octadiesel amine or copper chloride as a transition metal ion, the diffraction angle reduced to lower 2 theta, around 4.5 to 5.8. That means the nanoclay gallery has been swelled and expanded due to the modification in here, as illustrated in here. So after the in situ modification of nanoclay in UF resin, we can check the properties of the resin. Not much different in solids content of UF resin and also pH. Only specific, a little bit change in the specific gravity, but the big remarkable change in here we can see in viscosity. The viscosity of modified UF resin with nanoclay increase with higher nanoclay content and eventually reduce the gelation time of urea formaldehyde resin. So this is the scheme of the intercalation of nanoclay in low molar ratio UF resin. For the ODA, it was protonated, and finally when it is intercalated in UF resin, it will release hydrochloric acid and reduce the pH system of the pH of UF resin, and it will trigger the curing of UF resin. And for the bentonite, TMI bentonite, the copper ion will react with the hydroxyl groups on the surface of bentonite and release protons. This proton will have the reducing the pH of the UF resin and trigger the curing reaction of the UF resin. So when we check the crystallinity of UF resin modified with this bentonite, there is a decreasing in the change in the diffractograms and also decreasing in crystallinity. For the ODA bentonite, it decreased from 44% to 49, 54% to 49. But for the transition metal ion bentonite, modified bentonite, it decreased up to 35% of crystallinity. So it greatly reduced the crystallinity of urea formaldehyde resin. We know that urea formaldehyde is a thermosetting polymer. So it consists crystalline structure. So we can reduce the crystalline and produce more branch structure and the network structure for the UF resin after curing. So when we check the differential using differential scanning calorimetry for the curing temperature decrease when we add more nanoclay content into UF resin. So after that, we applied the adhesive into plywood, and it can produce greater tensile strength for plywood, either using ODA bentonite or TMI bentonite in here, and further reduce the formaldehyde emission of plywood bonded with modified bentonite, especially for 5% addition of modified nucleate. For the bio-based adhesive, in here we use oxidized starch-based adhesive, where the starch, the cornstarch, was sonicated and then gelatinized, and after that, oxidized using hydrogen peroxide at different ratio, and then we add the 15% of polyphenol alcohol and add block PMDI as cross-linker at different levels. After that, we use this adhesive to make or to prepare fiberboard, medium density fiberboard. We do the blending in the rotary blender and then do the mat forming. And after that, hot pressing at 185 degrees Celsius for 10 minutes. And then after that, with the conditioning according to the standards. This is the hot pressing schedule we use in here. So for the cross-linker, we prepare the block PMDI by blocking the isocyanate group of liquid PMDI using sodium bisulfite. And after that, we check the block PMDI compared to the pro-PMDI in here. We can see the isocyanate groups, the free NCO group appear in pure PMDI, but no isocyanate group in block PMDI. But after deblocking, reaching the blocking temperature around 78 degrees Celsius, according to the DSC analysis, we can get the free NCO back after the blocking of block PMDI. So it released the free NCO for reaction. So the oxidized starch itself were characterized at different level of hydrogen peroxide to starch ratio in here. We can see the formation of the carbonyl for the aldehyde and also carboxyl in here. And the degree of oxidation increase with increasing the amount of hydrogen peroxide, obviously. And based on the NMR, we can confirm the presence of the carbonyl of carboxyl group and also aldehyde in here, especially for high level of hydrogen peroxide. And then for the XRD, the crystalline structure of the starch, we can get the native starch is crystalline. It has crystalline structure, but after the oxidation, the crystalline structure was destroyed and changed the partially amorphous in there. Only one peak in here. So when we mix the oxidized starch with the block PMDI, and then we can get the curing temperature in here. It has two peaks, exothermic peak. The first peak, it was related to the releasing of free isocyanate from block PMDI. And after that, the isocyanate will react with the hydroxyl group of oxidized starch to form the amide linkages at higher temperature, around 120 degrees Celsius. And then, this is, as we can see in here, this is the liquid oxidized starch adhesive before heating, and this is after heating. It changed it become gel after curing. And after that, we can check the change in the functional group at different temperatures after mixing the oxidized starch with block PMDI. Oxidized starch alone, it only has a typical peak at 1720. It belongs to the carbonyl groups. And after mixing with block PMDI and mix and do the reaction at 100 degrees Celsius, the functional group changed. There is a formation of amide linkage in here at 1640. And then when we increase the temperature to 160, so it will form a fully cross-linking in here. So we can see the schematic, the illustration for the reaction between the oxidized starch with block PMDI. There is a formation of the amide linkages between the NCO group and the OH of the oxidized starch. When we apply this adhesive, we use this adhesive for making fiberboard, medium density fiberboard. We can see that addition of block PMDI at 7.5% produce fiberboard with a comparable properties to the conventional fiberboard. The conventional fiberboard in here, they use UF resin, UF formaldehyde. So we can produce fiberboard with comparable properties to the conventional one, but with very low, almost zero formaldehyde emission. We can see that the fiberboard here, using urea formaldehyde, it has around 0.8 milligram per liter of formaldehyde emission, but for the oxidized starch bonded fiberboard, it is around 0.02 or 0.03. That's because of the biogenic formaldehyde from wood itself, not from the adhesive. So the last part is the natural rubber latex adhesive in here. So we mix natural rubber latex with polyvinyl alcohol and add PMDI as crosslinker. So we prepare the adhesive and then we use the adhesive to prepare plywood for cold setting. So we don't use high temperature. We prepare the plywood at room temperature for 24 hours. And then we do the characterization. For the properties of the adhesive in here, we can see that the solid content of the natural rubber latex adhesive increase with increasing the PMDI content. The viscosity obviously increase because when we add PMDI, it will change the phase from liquid to gel due to the cross-linking. And gelation time is getting shorter at room temperature and not much different in pH. So what happened when we mix? So there is a hydrogen bonding between the natural rubber latex with polyvinyl alcohol. And after that, there is a cross-linking between the NCO group with the hydroxyl group for the natural rubber latex and polyvinyl alcohol in here. So based on the DSC analysis, we can get the curing temperature of this type of adhesive at around 23 degrees Celsius in here at the TP. So when we use this adhesive to prepare plywood, we can get, there is an increasing in tensile strength of plywood with increasing the PMDI content in natural rubber latex adhesive. So it reached 1.0 megapascal, which higher than the minimum standard, where the minimum standard is around 0.7 megapascal. And then when we check the wood failure, it's quite good for the dry testing, but not for wet testing because probably the natural rubber latex and polyvinyl alcohol is not suitable for high moisture or wet application. So for the formaldehyde emission, it's really low. It's around 0.09 milligram per liter because we don't use formaldehyde in here for the natural rubber latex, but it comes from the biogenic formaldehyde of wood. So what happened when we add the PMDI in the natural rubber latex adhesive, there is a smooth formation in here, but without PMDI addition, it's very rough. It's difficult to form film of the adhesive, but with addition of PMDI, it can form smooth film in here. So as a summary, a lowering formaldehyde to urea mole ratio and using high initial FO mole ratio of UF resin can produce ultra low formaldehyde emission of UF bodied composites. And then intercalating of partial or partially exfoliating nanoclay in UF polymer during resin synthesis, it could lower the formaldehyde emission of UF bodied composites. And then adhesion performance and formaldehyde-free adhesive based on oxidized starch can be tailored by incorporating block PMDI as crosslinker for hot pressing adhesive. And finally, a formaldehyde-free and cold setting adhesive can be prepared by incorporating natural rubber latex with polyvinyl alcohol and then cross-link this base polymer with polymeric isocyanates such as PMDI. I think that's for my presentation. Thank you very much for listening.
Thank you, Pak Lubis. Very interesting. Yeah. Following your presentations, you described many or several interesting system. I guess that very close to our daily life nowadays. Yeah, we can find easily many wood products. Yeah, that been modified with several technology. I believe one of them may be the one that also you develop in your laboratory. So you introduced to us several systems regarding to the urea formaldehyde resin, with the wood adhesive properties, and then also you introduced to us about the bio-based adhesive, especially regarding to the oxidized starch adhesive, and also natural rubber latex adhesive. Yeah, we also really interested into this topic since in the daily life, if we come to the furniture industry or company, now we can find many variety of the wood products. And yeah, I do believe most of them may be already modified with a certain technology, yeah, using, I guess one or two of them could be related with the presentation that you just delivered. Even though, yeah, it's really surprising. You have the great strategy how to modify the properties of your composite system using the intercalations, yeah, of nanoparticles inside. So later on, maybe I have a question about that. All right. Again, thank you all much. Thank you so much to all speakers for your great presentation today, and to all participants. Now, finally, we come to the Q&A session. Yeah, for the question and answer, and I can check from the chat box here. It's already 2 questions from the participants. Maybe I can guide for all speaker. Yeah. First question, I guess it should be for properly. Yeah. The question from Wida Rahma. This my TV. So very great presentation. Properly, I have one question. Since the forward osmosis is said to be more environmentally friendly compared to reverse osmosis, will it replace reverse osmosis in the future, especially for seawater desalination? So properly, please.
Okay, I think this is a very good question. However, when it comes to the seawater desalination, I think RO process is better. Today, I presented good points of the FO process, but I think until now, it cannot compete with the RO process because considering the very high salt removal efficiencies of our RO, and RO system is more simple, and the maturity of the technology, considering the maturity of the technology, RO is a better process. But I think in the future, FO process and RO process can be combined together to reduce the desalination energy. And also when it comes to other types of the water, for example, very dirty water, which can contaminate the membrane surface a lot, then in that case, FO can be the better than the RO, because as I explained, FO process has an advantage in the membrane fouling part. So, and also if the salt concentration is really high, like the 70 gram per liter, more than 70 gram per liter, then FO process will be better than RO. So now RO is better, but it can be combined, and in different situation, FO can be better than the RO. Thank you.
Thank you, Probably. And Vida, if you're still here, so if you have any additional questions, I guess, yeah, it answer your question. And also to other participants, you can also directly deliver your questions to our speaker. Yeah, just raise your hand and then open your mic. Even you can turn on your video and then you can directly ask, yeah, to our speaker. So now let me try to move to the second questions. This is from Yustika. I guess the question for Propakor, yeah, regarding to the water treatment. In recent study, many studies are concerned with the water treatment using biomaterials, especially for coagulations and coagulation processes. Yeah, but beside the use of biomaterials that yeah, it guarantee for the environmentally friendly properties, that are there any other advantages compared to that also commonly used in water treatment? For example, aluminum sulfate, for example, and whether water treatment using biomaterials have been carried out in the large scale in water treatment or not. So please, Propakor. Hopefully you understand the question. Yeah, it's quite long.
Yes, thank you. That is also very interesting questions. And I think the major concern, right, with biomaterials now is the cost of production and also the scale of the production and availability, right, for commercial use. So yeah, it is in the early stage of development of this type of materials. Right? Therefore, the cost may be higher to compare with the existing product that are commercially used. However, right, there are many study and also many reports that show us or confirms about the benefit in terms of friendly to the environment, right? And if we have like active work in this field, right, the technology may be mature like in foreseeable time in the future, and the scaling up of production process will be available very soon, and the product with competing price, right, will be available in the future. Right. So to answer the question, I would say yes. At this moment, it is quite hard for biomaterials to compete, right? But the result from technical study, right, prove that the real benefit in terms of environmental friendly, right, is high compared to normal or the chemical that we use in the process now, right? The only remaining question is only scaling up the process and also availability in large amount in the future, right? But that will be coming soon, right? And in our lab, we actually also develop a process for scale up this production of these materials, right? That also receive funding from industry, right? So they have a promising future actually. To answer the question. Thank you.
Yeah, and keep going for development and innovation, yeah, bro.
Right.
I guess before we move to the next question, there is one question come to my WhatsApp group. I don't know why she didn't deliver to the chat room. I guess it's still for Propacor. So chitosan is well known as biocoagulant in water treatment, but sometimes we need to disperse chitosan in acetic acid solution, which may change the pH of the water. Right. So is there any treatment we can do to overcome this?
Okay.
Yeah, please, Prof.
Yes. Very good questions. The conversion process by converting chitosan into quaternized chitosan is very effective. We can, when we introduce the positive charge into the structure, right, it is completely soluble in water at any pH without the use of any acid. Yes.
Yeah. So that's the strategy, yeah, to overcome the pH dramatical change. Okay, thank you, Prof. And then yeah, we still receive several questions in the chat room, and the next question, I guess, this is for Miss for Pak Adli. Maybe Pak Imran really impressive with your presentation, Pak Adli. What's the software did you use to make beautiful figures? Yeah, it's really inspiring for our participant. Yeah, he really.
Excuse me. Hello, excuse me.
Okay, sure, please. Is this Imran who's speaking? Hello.
No, I think not.
Oh, no? Okay.
Yeah.
So maybe you can reply, Pak Adli.
Yeah. Thank you, Mr. Imran. I just use a Sigma plot software. I got it from my supervisor, Professor Byung Dae Park from Kimbok National University. So I use that until now.
Yeah.
You can use that. You can use all.
I have question.
Okay, you can raise your hand, please, so we can easily indicate who you are. Okay, Mohbet Ali. Okay, please.
My question.
Ali. Yeah, please.
My question is that pH is why 1 to 14.
Yeah. What's your question is?
pH is why pH 1 to 14 range.
Oh,
pH, power of hydrogen solution
oh yes. Why is pH is 14?
is 1 to 14.
Ah, so may I know you? Where are you from, Muhammad Ali?
From Pakistan.
Oh, from Pakistan. Very amazing. Okay, thank you. You would like to know the reason why the pH is ranged from 1 to 14?
1 to 14.
Yeah, to whom your question would like to deliver? To Propakor? All right. I guess maybe I'm not sure this related to the content that delivered in presentations. It's just like maybe the normal question, Prof, regarding to the pH. Why the pH is scaled from 1 to 14? Do you want to reply the questions? Or if not, maybe we can move first, yeah, to the question just already listed in the chat box.
I'm sorry, Prof. I think the connection, Dr. Fitri, is trouble. Wait a moment. I will go to the Dr. Fitri room.
Okay, sorry for the inconvenience. Maybe we can continue to other questions. Here are some questions for from Siti Robiah. I guess the questions is for Prof. Lee. Okay, thank you for your presentation, Prof. Lee. It's the first time I heard about forward osmosis. Mostly I heard reverse osmosis or ultrafiltration for water treatment technology. I have one question regarding FO. In your presentation before, you show that FO can be used before RO in seawater treatment. Is it possible if we reverse the position, RO first, then FO as the next stage of filtration for brackish water from RO because the concentration is lower than seawater?
I think this is also very good question. Recently, we are trying to find the application field for the FO, and in the previous question, I mentioned that FO and RO can be combined together. So the question suggested the RO can be, is it possible to use the RO first then FO? Actually, I don't exactly understand the meaning of the question, but the changing the position or combining with the other process is a very good try to develop new types of the water treatment processes. So I think that this is a kind of a bright idea to think about other way to combine different water treatment process. So I think depending on the proposal, the position can be changed.
Oh, all right. So sorry for just sudden interruptions due to the internet connections. Prof. Here is very cloudy, so soon it will be heavy rain. Then we can continue to another questions from Muhammad Reza. Muhammad Reza is a lecturer at UIN, one of national university in Indonesia. The question is for Prof. Lee. So my previous study was improving hydrophilicity of ultrafiltration membrane. Then the water flux is improved. It is quite hard to ensure the improvement of rejection. So would you like to share for us how you solve this issue in your recent work? Thank you in advance. And maybe later on, Propakon also can comment, yeah, related to this.
Okay, I think for the osmosis membrane and RO has a similar property, but it is the different property with the UF filtration. In case of UF, the main removal mechanism is the size exclusion, but for the reverse osmosis and for the osmosis, the main important property is diffusion of the solute through the membrane. So when we improve the hydrophilicity, we could improve the water flux. But in that case, we improve the hydrophilicity of the structure, the support layer. Here, the support layer is very similar to the UF. As you mentioned, when you increase the hydrophilicity, you could improve the water flux. And in case of the UF or RO, I mean, in case of the FOO, we could also improve the water flux when we change the hydrophilicity of the support layer. But for the rejection part, we have to change the polyamide thin film composite recipe. So the main rejection is from the active layer, not the support layer. So I think that's why the area is a little bit different between the UF and FO. Okay.
All right, thank you. Propakon, do you have any additional comment for the question?
Yeah, I think Professor Lee already clarified that issue.
All right.
Thank you. Yes.
All right, thank you. And we still invite all participants who still want to deliver questions to our speaker. So during the waiting the questions, the next questions from the participants, I have several questions. So firstly to Pak Adli, I really interested with the system of intercalations of nanoparticles, yeah, into your system, especially in the bio-based, if I'm not mistaken. So if I'm not mistaken, I follow from your presentations. One time the intercalations of the nanoparticle to your material occur, then it improves the adhesive properties, right? So what actually the mechanism behind why it can be occur?
Okay, thank you very much. So the intercalation was done in UF resin polymer. That's a synthetic one, not the bio-based. So it's a synthetic UF resin. So we did addition of nanoclay during the synthesis, and then theoretically it will disperse and also intercalate in the UF polymers. So after that, there is a two mechanism. First, the dominant mechanism is a physical interaction. Yeah, that's the dominant one. And then after that, due to the modification of nanoclay, we use the transition metal ion, copper chloride, so that the copper ion will react with the hydroxyl groups of on the surface of nanoclay, and it will release proton that will reduce the pH of UF resin system. This will trigger curing mechanism. That's the chemical reaction. Something like that.
Yeah.
That's but the dominant one is the physical interaction between the nanoclay with the UF resin to increase the viscosity, and then after that, faster the curing of the UF resin, something like that.
Yeah, so I mean physically and chemically the mechanism was occur, but predominantly physical interactions. Thank you, Pak Adli. And other question for Pak Adli. Sometimes,
ma'am, why you were laughing at me, ma'am?
Sorry, Bu Mita or Bu Amel, can you mute? Yeah, thank you. And then the questions for Pak Lubis again. So sometimes natural polymer susceptible to the degradation. So how to overcome this issue?
Yeah, thank you very much. That's why we need to work together with industry, because in research institute we focus on development of bio-based, sustainable, but in industry they don't want it because it's still expensive and also susceptible to biodegradation, something like that. So in wood-based composite industry, still if they use bio-based source, they use lignin and tannin as a substitute to the phenol in phenolic resin. That's the what does it say? Almost 100% substitution of phenol in the wood adhesive. So in other, such as oxidized starch, natural rubber is still in development. So how to overcome that? Usually, the bio-based, the wood-based composite will overlay with melamine overlay or high pressure laminated to increase the water resistance. So first, they will increase the water resistance, so prevent the prevent the water to enter the wood-based composite. So it will enhance the biodegradation or susceptibility to degradation, biodegradation, something like that. But it's still difficult to accept the bio-based adhesive in wood-based composite industry, except for lignin and tannin as a substitute for the phenol in phenolic resin.
So it means the most strategy is to improve the hydrophilicity of your materials, so can prevent the water attachment.
Hydrophonicity, to prevent the water. Usually with overlaying the
or coating, maybe,
something like that. Coating.
All right. And I have a question to Prof. Pakor. From your first system regarding to the magnetic framework composite or MFC, I'm really wondering with your material, Prof, in which one time the MOF composite with the magnetic nanoparticle, I can see from your result, it exhibit really extra huge surface area, yeah. So where actually that properties come from? Even though from the hysteresis, I can see from the BT curve, from absorptions, also it indicate the significant modifications in terms of the surface area properties of your composite material. Then it lead to the great absorption capacity, properties.
So actually, if we compare the surface area of the composite particles, right, with the neat MOF, it is lower, right? Because the surface area is normalized by the weight of the materials, right? The magnetic particle core, right, it's actually has higher density than the MOF, right? So it's lower, right? But it is the area is higher than the pure magnetic particles, right? Because of the MOF layer on the surface, but lower than the original MOF.
Oh, if we normalize it,
right?
Because it reached to 1,000 something, if I'm not mistaken, from your data. Yeah, it's quite high. All right. Still any questions from the participants? So we would like again to invite all of you, if you still have any questions or comment to the presentation, just delivered by our three speakers. So you can open your microphone, and then raise your hand. You can directly deliver the questions to our speaker. Please. Still any? No questions anymore? Oh, attendant links. Yeah, okay, please kindly wait. All right. And is there any still questions to all participants? If you don't have any other questions, I guess we almost come to the end of this seminar. Yeah, very attractive. Yeah, many questions come. And then maybe before we close this session, I would like to give several minutes or to each speaker to deliver the closing statement. Maybe we can start from Prof. Pakor and then continue to Prof. Lee and then Pak Lubis. So please, Prof. Pakor.
Yes. So First of all, I'd like to thank Professor Fritri again for organizing such a very wonderful series of seminar here, and this is a very good opportunity that we can share our research work and also get to know some very interesting work from Professor Lee and Professor Adley as well. I thank you very much for your wonderful talk, and also thanks for all the audience for joining us today. Thank you very much.
Thank you, Prof. Pakor. And then next to Prof. Lee, please.
Okay, this is a very interesting experience for me to attend this online seminar, and I'm very impressed, very well organized this seminar. So if I can attend, I'd like to attend in the future again. And also it's good to know the other topics of the research from the other speakers. So I think I have to try more to study and to conduct research well. Thank you.
Thank you, Prof. Lee. And then finally, Adli, please.
Yeah, thank you very much, Dr. Putri. Yeah, thank you very much. It is my honor to be the invited speaker in this conference. This is the first time I was invited by the committee to be the invited speaker. Usually, just an oral presenter attending the seminar sometimes, but this is really wonderful. Thank you very much to Dr. Fitri, the committee, and also all participants. Thank you very much.
All right. Thank you again to Prof. Pakor, to Prof. Lee, and also Pak Adli. On behalf of Department of Chemistry, and also the committee of this program, I also would like to again sincerely thanks for your great contribution on our second seminar. We really had a great time today. And yeah, I guess all participants also learn many great things from your current research work. And yeah, we do hope as the outcome of this program, it can inspire and bring some motivations, especially for our students and also other participants from other institutions to develop as well as to improve our research work. And yeah, hopefully by the end it can come to the great publications. And before we close this session, I guess the committee already prepared the certificate, but still electronic certificates, since we conduct the seminar through online. So here I would like to deliver the e-certificate for Associate Professor Pakor Prakarshit. Again, thank you so much, Prof, for your
Thank you very much
and priceless support to our program. As well, Prof. Sun Lee, even though on your great holiday, you you prefer to stay with us here, for seminar. It's more than priceless. Thank you so much for your great availability. And I do believe we still have many great opportunity in the future, to meet again in the better situations and the better occasions. Thank you again, Prof. Lee. And then finally here the e-certificate for Bapak Muhammad Ali Lubis. Pak Adli, even though we never meet people directly, but I deeply appreciate your great contributions in this seminar. Thank you for your great sharing for us. And again, hopefully we can very soon meet in the real in the real world. Hopefully also we can find some possibilities in the future for collaborations.
Sure.
Yeah,
thank you very much.
And that's all. And here for the participant, the attendant link, please kindly put your information through this link, or even you can scan. Here the codes for your attendance, and soon after this conference, we will provide the certificate of your attendance on this seminar. And last but not the least, I do apologize if there is any inconvenience during hosting this conference or seminar. And again, thank you very much to all participants who has consistently participating our program. And we would like to welcome you back. Here is our flyer for the third seminar. again, we will have Propacorn with a different topic, yeah, that he would like to share with us still regarding to the polymer composite. And also we have two other speakers, yeah, from Institute Technology of Surabaya. This working as well with the membrane composite, yeah, with consists of polymeric membrane with the inorganic pillar, and also another college of Pak Lubis from BRIN, yeah, Ibu Atanasia Amanda Stefani. And yeah, we've been informed Propacon the SIP schedule, yeah, become earlier due to the special occasion for you. And then Bu Amanda just informed she will be in Italia on the conference for one next time, because yeah, maybe she has a kind of business trip from her office. But yeah, very glad to hear that she also available on the modified depth. Yeah, and yeah, I really wish all of you, especially our speaker, a great health, yeah, and also great happiness, and very looking forward to see you again. Yeah, thank you so much. Thank you so much. Very good afternoon, everyone. Thank you. Thank you, Prof. Thank you.
Thank you very much.
Thank you very much. Thank you.
Thank you.
Thank you.
See you soon.
Yeah, see you pretty soon. Alright. Ya, Pak Adli, terima kasih banyak.
makasih,
Sangat
Bu.
menarik. Mudah-mudahan nanti bisa berdiskusi.
Ya,
Ya.
semoga bisa berkolaborasi.
Iya.
Ma'am, when we get certificate?
Sure, you can get it. Yes, fulfill the attendance link, please.
Terima kasih, Pak Adli.
Ya, terima kasih. Terima kasih.
Termohon Bu Fitri, sukses, semangat.
Oh, terima kasih. Terima kasih, Pak. Terima kasih banyak. Ya, terima kasih Bapak Ibu atas kehadirannya. Ditunggu kembali untuk seri webinar berikutnya atau seminar berikutnya di tanggal 5 Oktober 2021. Terima kasih banyak. Mohon maaf bila ada kekurangan. Insya Allah sertifikat akan segera terkirim ke email atau kontak Bapak Ibu yang disediakan pada attendance. Ya. Ya, segera akan kita close Bapak Ibu untuk linknya hari ini. Terima kasih banyak, semoga Bapak Ibu sehat selalu. Terima kasih telah berpartisipasi dalam rangkaian kegiatan seminar World Class Professor ya untuk seri yang kedua, dan kegiatan ini disupport secara penuh dari Kementerian Pendidikan dan Kebudayaan riset dan teknologi ya. Mudah-mudahan bisa bermanfaat untuk Bapak Ibu semua, dan selamat berjumpa kembali nanti di tanggal 5 Oktober untuk conference berikutnya. Saya
Sorry.
saya akhiri. Assalamualaikum warahmatullahi wabarakatuh. Selamat sore, selamat beraktivitas dan selamat beristirahat untuk Bapak Ibu semuanya. Terima kasih.